Today we're going to talk about section 8.6, linear programming. I'm actually going to split this section into two parts. So the first part is going to be today, and the second part's notes will be posted on Wednesday. We're going to have a slight change in the quizzing for this week. I will send an email later today with more information just because of the holidays that are going on this week. So I will keep you guys posted with that. So today we're going to talk about this situation over here. So you're the owner of a furniture shop, Funky Furniture, which specializes in full-size Lego-inspired furniture. You'll be making chairs and tables as pictured below, and they must look exactly like the pictures. So we want to look at some of the information that they're telling us here. So it says that for each chair sold, you're going to make a $10 profit. And for each table sold, you'll make an $18 profit. Each day, your supplier can only deliver 8 small components, which are 2x2 Lego bricks, and 6 large components, 2x4 Lego bricks. So if you guys look at this diagram here, the chair is made up of 2 small pieces and 1 large. And then the table has 2 small pieces on the bottom and then 2 large on top. So the first question that they're asking us is, what is the objective of the Funky Furniture situation? Write an equation that represents this objective. So an objective is a goal. So a lot of the linear programming problems that we're going to talk about in this section, you're putting yourself in the shoes of a business owner, and you need to figure out what is your goal in this situation. Now, they told us about profits, right? So our goal in this particular situation is to maximize profits. Okay, if you're ever talking about profit, your goal is to make the most money as possible. If, for example, you're ever talking about costs, well, costs you'd hope to minimize, right? But in this case, we're talking about profit, so we know we're maximizing. So to figure out the profit that we're going to make, I'm going to call it P equals. We know that it's $10 for each chair and $18 for each table. So those are going to be our variables. Most of the time I would ask you guys, what are the variables? Make sure you label them. So we use what's called let statements. That means let x equal and let y equal. So we're going to say let x equal the number of chairs and let y equal the number of tables. So if we're making $10 for each chair and $18 for each table, that means we're going to have a profit equation of 10x plus 18y. Okay. Now, obviously, we won't know the amount of profit we're going to make unless we can figure out how many of each item we should sell. Okay, and that's part of what we're going to be figuring out in these problems. So our next question asks, what are the constraints on your company? Constraints are like limitations. What's limiting our production? Depending on the scenario, you could be limited by money, you could be limited by time, space, labor hours, all sorts of things, okay? Now in this particular problem, they say each day your supplier can only deliver 8 small components and 6 large components, okay? So basically we're limited on the number of small components and the number of large components that we can have. So we need to come up with some inequalities that represent these limitations. Now we know that for a small, I'm actually going to go back up here. For the chair, we're going to be using 2 small components, and then for the table, that's also going to use two small components. So if I'm thinking about the total number of small components, let's actually write this down. So we know that the small components has to be less than or equal to 8, because we can only deliver up to 8. And the large ones has to be less than or equal to 6, because they told us we can't deliver more than 6. So if I were to come up with an equation or an inequality that represents these, in my chair, I've got 2 small. In my table, I've got 2 small. So that means for the small components, it's going to be 2x plus 2y is less than or equal to 8. So that means for each chair, I've got 2 small. For each table, I've got 2 small. And the total has to be less than or equal to 8. Our next inequality has to do with the large components. So I've got 1 large per chair, 2 large per table. So I'm going to say 1 large, it's 1x per chair, 2 per table has to be less than or equal to 6. So those are really the only limitations. The only other couple things that I usually mention is that you can only make a positive number of tables or chairs. So we can't have any negative numbers. So I say x has to be greater than or equal to 0, y has to be greater than or equal to 0. That's actually why my graph is only dealing in this first quadrant. It's because of the fact that we can only have positive values. Okay? Now, we need to graph these inequalities, and that's going to help us determine the feasible region. So the feasible region is the set of all possible points that we can have in a problem. Okay, so let's go ahead and graph each of our inequalities. Now I'm going to start with those two, grabbing my straight edge. Okay, so x is greater than or equal to 0. That's just going to be a solid vertical line shading to the right. Okay, instead of shading, I'm just going to assume we're using this whole section. Y is greater than or equal to 0. We're going to shade up. Again, same thing, I'm not going to shade. We know we're using the first quadrant. Now these other two, I need to mark some tick marks on my graph, just so things don't get super small. I'm going to go 2 units for each tick mark. Okay, and we've got these 2 inequalities up here. Now remember, there are some shortcuts when we're graphing. The covering up method helps us graph by intercepts. So if I cover up the x, I know my y-intercept is 4. If I cover up the y, I know my x-intercept is 4. And we're going to have a solid line. Okay, so figuring out where the shading is, if I were to test a point, let's say we plug 0, 0 in here, I would end up with 0 is less than or equal to 8, which is true. So I'm going to take my pencil and lightly shade in toward 0, 0. 0, 0 is below this line, so I'm shading in that direction. Now we're going to do the same thing for our second inequality. My y-intercept, in this case, is 3. My x-intercept, covering up the y, is 6. And we've got a line going through. Okay. And again, plugging 0, 0 in to figure out the shading, we end up with 0 is less than 6, which again is true. So I'm going to shade towards 0, 0. Now you'll notice that our solution region, I'm going to darken it, is the section that's overlapping. So we've got something like this. Okay, so we call this the feasible region. If I were to look at all of our possibilities, remember we can only make whole number quantities of stuff. I would look at the whole number intersection points, and those would be all of our possibilities. Okay, for example, so our x's were the chairs, and the y-axis was our tables. So I could make 4 chairs and no tables, and that would be fine. I could make 1 of each, and that would be fine. That would satisfy our constraints. We would still have room on the truck for our supplier. So any of these points, okay? Now our goal is to test each ordered pair. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different possibilities. And we're gonna test all of them in our objective function. So our objective function was up here, was to maximize profit. So I'll do the first one. I'm not gonna plug in 0, 0 because I know that we're not gonna make any money that way. But let's plug in the profit of 0, 1. That means 0 chairs, 1 table. I'm gonna plug in 0 in for x and 1 in for y. And I end up with a profit of 18. Okay, now what I want you guys to do is plug in every single one of these coordinates. Again, there's a whole bunch of them on here. And we're gonna see where our maximum profit comes. I'm gonna pause the video, go ahead and find the remaining profit values. Looking at our possible profits, we find that our most profitable situation is if we sell 2 tables and 2 chairs. And you'll notice that that comes from this value over here. Okay, so we call that point a corner point. Oops, sorry about that. So we have a corner point right here. Okay. And what you're always going to find is that your objective function will always be achieved by one of the 4 corner points, or however many corner points you have. Okay, so there's a video that I'm gonna post in Google Classroom that shows the reason why the corner points are always what you're looking for. So if we've got our objective function here, objective is always achieved at one of the corner points. So technically we didn't have to test all 13 of these. We only needed to test these 4 coordinates. And moving forward, that's all we're gonna have to do. So let's go ahead and flip to the next page and talk about what is linear programming. So linear programming is a process of optimizing a linear objective function which is restricted by a system of linear inequalities called constraints. Remember that the objective is always going to be your goal. Your constraints are your limitations. Okay, so the graph of the system of inequalities, the constraints, is called the feasible region. We saw on the previous page that the feasible region is representing all of the possible production values. How much of each item can you produce and still fit your constraints? So our corner point principle, which we just talked about, says the optimal values, maximum or min, of the objective function will always occur at the corner points of the feasible region. Now, there are some situations where we have a bounded region. That means it's closed in. And actually, the example we just did on the previous page is an example of that. Like if I have something that looks like this, and our final shading is inside, this is called bounded because it's all closed off. So we would test the 4 corner points, okay, in the objective function, okay? So we would test corner points in objective function. Okay, now an unbounded example, well, what if your shading looks a little bit different? What if we had, let's say I have a line that looks like this, and then a line that looks like this, and our shading was above both of those. So let's say our overlap looks something like this. Okay, totally realistic example. We still would test the corner points of that shaded area, but we would only be able to test these 3 because there is no maximum, okay? Chances are something like this would be about minimizing your objective function, okay? Now, part of the first section that we're covering today is just going to be setting up these equations, or, given a good amount of information, how could you draw a graph? We're going to wait until Wednesday to do an entire problem from start to finish. So the first thing we want to do is figure out how do we use let statements to just assign the variables and talk about the constraints. So a biologist needs at least 40 fish for her experiment. She cannot use more than 25 perch or more than 30 bass. So we have 2 different types of fish. So we're going to let x equal the number of perch and let y equal the number of bass. Now let's talk about our limitations. It says here she needs at least 40 fish. Now 40 fish means the total, okay? The total has to be at least 40 fish. Can we have more? Yes, we can, but we cannot have less than that. So we're gonna say that our first objective is that the total number of fish, x plus y, has to be greater than or equal to 40, okay? Now our next objective says we can't use more than 25 perch. So x has to be less than or equal to 25. Can't use any more than 30 bass. Y is less than or equal to 30. Now our last little bit is that you can only have a positive number of fish. So x and y both have to be greater than or equal to 0. Okay. Now one of the ways that I can express this information is by putting it into these inequalities, right? So this tells me that the number of perch has to be between 0 and 25, has to be between 0 and 30. It's a little bit more simplified than writing out separate inequalities, but this would be fine too. If you didn't include this part and you had these two inequalities, that would be perfectly fine, okay? I'm gonna have you guys give the next one a try. I will put up the answers in just a moment. All right, so we've got let X equal the number of mopeds, let Y equal the number of bicycles. So we have to produce at least 10 mopeds per month, but we cannot produce more than 60. So X has to be between 10 and 60, so I use that inequality. With the bicycles, the only limitation is that they have to be less than 120, so I have that right here. Again, accounting for the fact that the bicycles have to be greater than 0. And the total has to be less than or equal to 160. So these would be our constraints for this problem. All right, let's go ahead and jump to the next page. And here we have a problem where I'm giving you the objective function, I'm giving you the constraints, and we just need to find the maximum and minimum values. So our goal is always going to be to graph the constraints. Okay, so if I were to graph, I'm actually going to do this bottom one first. So notice that my x-intercept would be 6. My y-intercept, let's see, divide by 4. It's 4.5. So I'm actually going to mark up my x-axis 2 units for every tick mark. It's just a little bit cleaner. Okay. So I'm not going to bother graphing these first two because I know that that just tells me I'm in my first quadrant, which is all I have here anyway. This next one, my y-intercept is 5 and my x-intercept is 5. So I'm going to plot those points. And we have a solid line. And testing 0, 0, if I were to plug 0, 0 in here, I have 0 is greater than or equal to 5, which is not true. So I'm actually going to shade above this line, away from 0, 0. Let's do the same thing for the next line. My x-intercept is 6. The y-intercept we said was 4.5. Get the straight edge on there. And again, testing 0, 0, I have 0 is greater than or equal to 18, which again is not true. So I'm going to shade above pink line, away from 0, 0. Now, if you look at the overlapping region, it's basically above the pink on this side and above the blue on the left side. So I'm going to shade that in just a little bit darker. Okay, so our vertices for this overlapping region occur right up here at this blue point. So that's 0, 5. We have one of our vertices right over here. That's 2, 3. and finally at 6, 0. Okay, I'll go ahead and highlight these on the graph. They're a little bit easier to see. Okay, so we have 3 vertices. Now what we need to do is plug these vertices into our objective function. So I like to say C, probably representing the cost, and then we're going to plug the x in for x and the y in for y for all 3 of these. So our first situation, we end up with a cost of 30. Our second coordinate is 28. And finally, 30 again. So our maximum value, the value is always going to be the y value we're talking about. 30. When we have 0, 5, and 6, 0. Our minimum value is 28 when we have 2 and 3. So let's say this problem was referring to the total cost for producing bicycles and mopeds, just kind of like that previous problem. If this was our cost function and we tested our intersection points, our goal is to minimize cost. No company ever wants to maximize how much money they're spending. So cost is how much we're spending. So we would probably produce 2 of the first object and 3 of the second object. And that would help us find that minimum value. I'm going to be updating the homework this afternoon. So I would say just copy the notes for now. And by Monday afternoon, the notes the homework will be posted. All right, guys, stay tuned for your email. I will be sending an update for what this week is going to look like. Have a great day.